Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week, and this is going to be extremely math intensive. I don't do this very often because I know that not all of you enjoy this. I don't know exactly what the ratio is of people that enjoy it versus the people that don't enjoy it, but I suspect that there's an awful lot of people that don't care for math and that I would never want to do this on a regular basis. If you absolutely despise mathematics and despise calculus or even the thought of it, you really need to turn the video off now, okay? There's better things you can do that you would enjoy your time doing, all right? But if you're one of those nerdy folks that every once in a while likes to be exposed to how mathematics applies to meteorology, then hopefully you will find this somewhat interesting, okay? So we're going to be talking about something called moisture flux divergence, okay? And this is a term that I learned about at Penn State way back in the mid and late 70s. And it has to do with how moisture is accumulating or not accumulating in a given area. You might look at a weather map and you'll see really high dew points along the Gulf Coast. So there's a lot of moisture down there. And then the values will decrease as you head north. And then in the northern plains, you'll see a little pool up there of higher moisture content. And you're sitting there thinking to yourself, wait a minute, if the source regions of the Gulf of Mexico and those high dew points are coming north with the south wind, then why do they disappear in Oklahoma and Kansas and reappear as you head up toward Iowa and Minnesota? Well, it's because the wind field is convergent and it's actually pooling moisture in a given area. The moisture levels are increasing, and so you get these little islands of higher dew points simply because of the fact that the wind pattern is convergent. So we're going to take a look at moisture flux and how that flux is either convergent or divergent and the math that goes along with that. So let's get started here. So we're going to talk about vectors and scalars and divergence, okay? Now, a vector quantity is one that has magnitude and direction. The wind is a great example of this, okay? The wind has a magnitude, how many miles per hour or knots it's blowing, and it has a direction. It's coming from the northwest, the southwest, the northeast, or whatever. So a vector quantity has both magnitude and direction. A scalar quantity only has magnitude, okay? And so that would be temperature, moisture, something like that. It has a value, either high or low or in between somewhere, but it's not oriented in any one direction, okay? So that's a scalar. And the wind, and we've talked about this before, unless you're a new subscriber and you haven't seen this, the wind, which is represented by this V, capital V here, and this is like a southwest wind, has two components to it, a U component, which is along the west to east direction, and a V component, which is along the south to north direction, okay? And a lot of calculations in meteorology are made a lot easier by splitting the wind up into these two components, okay? Now, this Greek letter here, the del operator, if you will, this is called a vector operator. It's not actually a vector, it's what we call a vector operator, and it also can be defined as the gradient. And you know what the gradient of something is. Like for instance, if it's 30 degrees in Henderson, North Carolina and 70 degrees in Lumberton, there is a strong temperature gradient or difference between those two locations over a relatively short distance, okay? So the del operator is a vector operator which can also be called the gradient. It's taking the gradient of whatever parameter you're looking at. So if you look at this here, the gradient of Q is going to be this operator, which is the change in whatever you're looking at with respect to x and the change in whatever you're looking at with respect to y. So you're going to have dq dx plus dq dy, okay? And moisture is a scalar, but when you apply this vector operator to it to get the gradient, you get a vector, okay? And the gradient vector always points toward higher values, and it points in the direction that the values in that parameter are increasing the most quickly. So if you have a bunch of equal temperature lines, isotherms that are oriented east-west, the quickest way to get to a higher value is to move in a line perpendicular to those lines of equal temperature. If you move at an angle, it's going to increase, but it's not going to increase as fast, okay? So you want to be looking, the gradient vector is going to be pointing perpendicular to those lines of equal temperature, equal moisture, or whatever, okay? And that's the direction the gradient vector points. Now, you can also do something called a dot product with the del operator. And if you take the dot product of del times the wind, then you get the change in the u component of the wind along the x-axis and the change in the v component of the wind with respect to the y-axis. Now, in this case, okay, we are looking again at the change in u with respect to x, change in v with respect to y. So this is the dot product of a vector operator and a vector, but that gives you a scalar, okay? Because the divergence of the wind is simply a value. It's not oriented in any one direction. It's simply a value. It shows you whether or not the wind is converging or it's diverging. Now, if it's diverging, then something has to come in to replace it. The air usually sinks. That's associated with fair weather. Or if it's convergent, then the air can't go down into the ground, so it has to go up. And if you've got enough moisture present, then you will get clouds, precipitation, showers, thunderstorms, and whatever, okay? So the dot product of the del operator and the wind field is called the divergence of the wind, okay? All right, let's move on ahead to the next slide here. So if you multiply the wind times the moisture, that's called moisture flux, okay? And that's what we want to be looking at ultimately here is the divergence of the moisture flux. Supposing you have a box, okay, and the box is porous, okay, the air can move through it. Well, supposing you're moving more moisture in from the one side than you are pulling it out on the other. So that would be positive moisture flux. The values of moisture are increasing in that box because there's more coming in than there is going out. Or if there's only a little bit coming in and a whole bunch going out, that would be negative moisture flux because the overall values are decreasing because you don't have as much coming in as you add leaving, okay? Now, if you take a look at v dot del q, and let's go back here because I believe that we had this here. Okay, so this is the gradient of q, okay, and we're going to be taking a dot product of the wind times the gradient of q, okay? And this is called the advection. And we talk a lot about cold advection, warm advection. If you have cold advection, you have winds carrying colder values toward warmer values. And if you have warm advection, you have warmer values moving in the direction of colder values, okay? In this case, we're talking about moisture advection. So it's either getting drier or it's getting more moist, okay? So if you split this up, and by the way, this minus sign here is simply something that scientists a long time ago decided to add because, like if you think about it with respect to temperature, a minus sign makes sense with cold advection because it's getting colder, and a plus sign makes sense with warm advection because it's getting warmer. Well, if you didn't put that minus sign there, it would be exactly the opposite. So this is simply a fudge factor, if you will, to make things make more sense, all right? So you have a minus sign, and if you split this up, this is the u component of the wind times the change in moisture along the x-axis plus the v component of the wind times the change in moisture along the y-axis, okay? And the magnitude of that advection is going to be the value of the wind times the value of the gradient times the cosine of the angle between them. Now, think about this. Let's say the gradient, you have east-west temperature lines, so the gradient will be pointing due south toward higher values, perpendicular to those lines. And if the wind is coming from the north and blowing in the same direction the gradient is, then the angle between those two is 0. And the cosine of 0 degrees is 1. If they're perpendicular to each other, then the cosine of 90 degrees is 0. So there's no advection, okay? So you want the wind blowing, if you want strong advection, you want the wind blowing as parallel as you can or as close to the direction as the gradient is pointing, okay? All right, so the divergence of the moisture flux, which is what we're ultimately after here, can be split up into two terms. The advection of the moisture, d dot del q, plus the moisture times the divergence of the wind, okay? And we're going to split these up into two, talk about them separately, and so that hopefully it will make some sense in a real-world situation. So we're going to start off with the minus v dot del q, the advection of moisture. Now, if the wind is coming straight from the north, there is no U component of the wind. There's nothing blowing from west to east, not even a little bit. So you can take that term out of the equation altogether. This U dq dx is gone. Forget about it. Over here, we have V times dq dy. Okay? Now, here's that term here. V is negative because along the y-axis, you want to take a look from south to north. Okay? Well, the wind is blowing north to south. So V is negative, and dq dy is also negative because the Q values are getting larger as you go south, but that's the minus y direction. The plus y direction is this way. So dq dy is going to be a positive over a negative, which is a negative number. So you multiply those two together, a negative times a negative, and you get a positive. And then you put the minus sign in front of it with the fudge factor, and that tells you that you have negative advection or dry advection, which makes sense because lower values here, higher values here, the wind is blowing from the lower values toward the higher values, so you are drying out the air over this location right here in the middle, okay? So the advection term is negative, which means things are drying out. Okay, now let's move to the second term, which is the convergence term. And that's going to be Q times the change in the U component of the wind with respect to the x-axis plus the change in the V component of the wind along the y-axis. Well, and this is where it gets a little complicated, and I can even see myself confusing myself here trying to explain it. But dV dy is going to be negative, okay? Now, why is that? Okay. So here is a wind which is stronger than this wind here, okay? So we have a negative wind, a negative V wind here, and as we move along the y-axis in a positive direction, then it's becoming even more negative, okay? So dV dy, the V is becoming more negative as you go from south to north, and the y is becoming positive. That's the way the y-axis is defined. And so that's negative, and so you have negative divergence or positive convergence, okay? And again, minus signs tend to correlate more with things coming together as opposed to things going apart. And so in this particular case, we have positive convergence, which means that the wind field is actually accumulating moisture. Now, I did not have time to actually go through and do a hand calculation and add all of this up, but these things actually appear to be competing against each other in this particular case because you've got dry advection, okay, but you've got a convergent wind field, okay, which is going to accumulate moisture. So the question is, which one of those terms wins out? And maybe I'll do another video sometime actually going through the actual calculations because you have to make sure that all the units are right, all right? Like for instance, water vapor is grams per kilogram, and of course, a lot of times with meteorological equations, the temperature is in Kelvin as opposed to Fahrenheit or Celsius, and so all those things, you need to make sure all the units are correct so that you get the right value, and that determines whether or not it's negative or positive. So that is the math behind the divergence of moisture flux. Okay, I promise I won't do anything like this again for a long time, but I hope you found it at least somewhat interesting. And the nice thing is about these videos is you can go back and watch this as many times as you want if you're curious, and it'll make probably a little bit more sense each time you do it. If you're not curious, then you don't want to watch this over and over again because it will be unadulterated torture. Okay. All right, folks, that's it for now. That's bonus weather video number 2 for this week. Hope you enjoyed it. And number 3 coming up Friday. Next daily weather update coming up tomorrow. You all take care, folks, and we'll talk to you soon. See you later.